35. Lucky man's getting a bit. That was just. As NTSB investigators pore over the wreckage of the failed bridge at the Florida International University near Sweetwater, Florida, one of the first things they're going to have to figure out was how this bridge was originally designed, and then how was it constructed. So today we're going to take a look at the original design of the failed FIU bridge in a way that all of us can understand. But first, let's take a look at a more conventional pedestrian bridge I stumbled upon on a recent layover in Hong Kong. Amazing engineering designs surround us all the time. I'm here in Hong Kong, near the Hong Kong airport, the long layover hotel with my day job as a 777 FO, and I found another pedestrian bridge that dimensionally very closely resembles the dimensions required for the design at the failed FIU bridge. This conventional looking pedestrian bridge spans about 180 feet and is about 60 feet wide at the walkway. Let's take a closer look. For this bridge, we have a double truss type structure all made out of steel using steel pipes and I-beams, with the connections all made with welded joints. The covered deck portion is cantilevered over using these structural members right here. And at the support columns is a plate structure located right there to allow for earthquake movement. Looking underneath the structure, you can see the two main support tubes spanning nearly 180 feet, four lanes of traffic. And the concrete is poured into these trays, a lightweight concrete mix to create the walkway. The concrete is not part of the structure, but is rather supported by the structure. Now here's another way to skin that cat, kind of a one-sided design that allows for a nice open design out towards the water. Here's your truss member on one side, and the rest of the bridge is cantilevered over. Looking underneath this structure, we can see how the walking platform is cantilevered over to one side. Again, the concrete filled in these trays, and supports including earthquake protection plates at the base. That allows the structure and the column below to wiggle around and not drop the bridge. Yes, I assume this is all Chinese steel since we are here in Hong Kong. And of course, the one thing you got to do with steel is keep it maintained, keep it painted to avoid rust and corrosion. Now let's return to Blanco Lirio World Headquarters in rainy Northern California and take a closer look at how the main span of the FIU bridge in Miami was designed to be built. Welcome back to Blanco Lirio Global Headquarters, where we're finally drying out after a big series of rains. My name's Juan Brown. You're watching the Blanco Lirio channel. So if the example pedestrian bridges I showed you in Hong Kong were rather conventional steel truss design bridges, how would you describe the main span of the failed FIU bridge? Well, if you look at all the design elements, it would be best described as a precast concrete post-tension, modified I-beam, asymmetric, non-redundant single truss design. Now that's a lot of words to describe a simple pedestrian footbridge. Let's break down all those different elements today in a fashion that we can all understand. First, let's talk about the precast element. This is an essential element of the ABC accelerated bridge construction method. This allows constructors to build the bridge off to the side of the road, very near where they're going to swing it into position and only disrupt traffic for a mere 6 hours once they take this finished portion of the bridge and place it upon its columns. First, the support for the bottom of the forms for the deck is created. Then the forms for the lower deck, the bottom portion of the lower deck, are placed. Then the forms for the truss are placed. Here's the rest of the truss forms. Then all the steel and ducting for the post-tensioning is placed in the bottom deck, and then the bottom deck is poured. This is all computer animation, by the way, from MCM and FIG. Now, I believe at this point, the concrete for the truss is poured. Now the top deck forms are built, steel installed, and the top deck poured. Now let your concrete cure, remove your forms, and post-tension all your tendons, and your bridge is ready to move into place. So now let's watch a great clip on the theory, purpose, and function of post-tensioning in concrete structures from Professor Chris Burgoyne of the Structures Lab at Cambridge University, England.
So when I was trying to pick up the pile of books, I pre-stressed them with my hands by squeezing on the outside. We can't do that in practice in real beams, so what we do is to put some plates on the end and squeeze between those plates. How do we squeeze between those plates? Well, we run a cable through the middle and we tension that cable up. So what I've got here is a typical steel cable that we would put through a beam. It's got 7 wires twisted together to make it slightly flexible. It's anchored by means of some wedges in the end here, which grip within this collet. So when they're pulled into place, we can tension them up and we can pull on the cable, and the reaction to that pulling on the cable is a force between the collet and the plate on the end of the beam, which puts the whole beam into compression. Okay, so to show how a pre-stressed concrete beam works, I've built this model. And this model is made of separate blocks of acrylic material, and around the outside I've wrapped a yarn of aramid fibres. These yarns go round 10 times. They're tied off with a reef knot at the end over here. And what I'm then doing is I'm pushing this end plate away by using a spanner here on this nut, and that puts the yarns into tension, which puts the beam into compression. And this is the objective of the exercise. We're trying to get the compression force into the beam, and the yarn is merely the way of reacting that force. Now, with the beam in this position, I can put significant loading onto this beam before the beam starts to crack or to fail. So to see the importance of the yarn and the force that it generates for the beam, I can now cut this yarn and we'll see what happens to the beam in that situation. So I'm going to cut it here. And the structure completely collapses. So you can see there is no glue or adhesive or anything that's holding this beam together. It was purely held together by the pre-stressing force. In practice, there are 2 forms of pre-stressed concrete. The word pre-stressing refers to the fact that we're applying an external force to the structure before we apply the load to which the beam is going to be subjected. But we can apply the pre-stressing force itself before or after we have cast the concrete. If we do it after we've cast the concrete, we leave a duct through the middle of the beam, we thread the steel cables through, We anchor them, as I showed you earlier, with the wedges, and we stress the cable up, applying the force to the concrete. That leaves a gap between the cable and the outside of the duct, and we fill that duct with cementitious grout, which protects the cable against corrosion. This form of construction is called post-tensioned pre-stressed concrete because the stressing is applied after the concrete has been cast. Well, in pre-stressed concrete beams, we tend to use a lot of pre-stressing force. A typical pre-stressing force in a beam will be something like 10 times the weight of the beam itself. And if we're talking about a structure like a motorway overbridge, for example, that may weigh 5,000 tons. So that means that we will need something like 50,000 tons of pre-stress force present in the beam, which is the equivalent of 500,000 kilonewtons. This means that we actually have to have a lot of pre-stressing steel present in the beam to carry that force. And there is also, that means there's an advantage in using very high-strength steels. And we typically use pre-stressing steels which will have strengths between 1,700 and 2,000 megapascals, which is something like 5 times as strong as conventional reinforcing steel. And this means that pre-stressed concrete structures typically use less steel than a reinforced concrete structure doing the same job, which is an additional advantage of using pre-stressed concrete.
Did you notice what the professor said about the typical tensioning you put in an I-beam? 10 times the weight? On a 950-ton structure, that is a lot of tension. So why is so much steel and post-tensioning required in concrete design? Because concrete is strong in compression but weak in tension. Particularly with this design, a modified I-beam design, where the top structure is in compression as loads are applied, and even under the dead weight of the structure, and the bottom of the structure is under tension, which concrete does not like, requiring much more steel and reinforcement and post-tensioning in the bottom deck of the structure than in the top deck. Let's go take a closer look at the plans. So here's a cross-section view of the modified I-beam design of this structure. As the designers said, they were going to redesign the I-beam, and this is what they came up with. They've created an elegant-looking design where the main design elements are the structure. Instead of having a big, bulky, heavy structure to support the walkway and canopy, the walkway and canopy are now the main structure. This allows the main span to be self-supporting, and they can utilize the ABC method of bridge construction. The overhead pipes and pylon do not support the weight of the structure. There's no cables inside of those pipes. They merely add a little stiffness to the bridge to dampen any movement while folks are walking across it. In other words, the overhead cables and pylon and asymmetric truss design to match the cables are primarily aesthetic. A true cable-stayed bridge, by definition, supports the weight of the bridge. This design does not. The slender 2-foot thickness of the walkway allows designers to bring the bridge closer to the ground and reduce the number of stairs to get up on the walkway while still maintaining clearance underneath the bridge for traffic below, thus encouraging more use of the bridge. There's also elevators on each end of this bridge. Here's a side view of the plan for the main span spanning 175 feet. Generally, truss designs are symmetrical in nature to even out the loads. These truss members are asymmetric to match the overhead structure above. And again, this truss design is designed to support the entire weight of this span. Now let's look at the design for the post-tension tendons. The lower deck has 12 longitudinal tendons running the entire span of the deck. The upper deck or canopy has just 6 longitudinal tendons running the entire span, which makes sense as the upper deck is in compression and the lower deck is in tension, requiring more post-tension tendons. Each of these tendons are built up from a bundle of steel cable, each individual cable being 0.6 of an inch in diameter. The lower span gets a bundle of 19 cables, except for T6, the outermost one, which is 12 cables. And the upper span gets anywhere from 7 to 12 cables for each tendon. The lower deck also requires lateral post-tensioning, and here's the plan for that. These tendons are spaced about 2.5 feet apart, and each tendon consists of 4 0.6-inch diameter cables. By the way, this plan view shows the main span, the center pylon, and the second span. Here's a closer look at the transverse or lateral tendon profile, including the call out for the amount of strain and the tensioning sequence to be applied to each tendon. Here in the general notes is the rest of the specs for the tendons and the entire bridge, including the compressive strength of the concrete, 8,500 psi. See the link in the comments section to take a look at these plans for yourself. Now let's look at a short animated clip from LMK post-tensioning systems and show you how this hardware gets installed in the concrete structure. Now, I don't mean to imply that LMK was involved in any way whatsoever with the FIU bridge construction. It's just that they have the best animation to illustrate the hardware that's used in post-tensioning. Here's an anchor design similar to what you would see on the longitudinal tendons using multiple strands of cable. Note the steel reinforcement and the tube sticking out the end for grouting after the procedure. And here's an anchor you would see similar to the transverse or horizontal tendons, 4 strands on the lower walkway. This hardware comes in many shapes and sizes and does not represent the exact hardware that was used in the FIU bridge. Here's how these tendons are assembled. Note all the additional steel reinforcement in place before you even get to the steel cable tendons. Here's the ducts used to run the cables through. This is the plumbing used to apply grouting after the procedure. The grouting seals the tendons to prevent corrosion. Additional bursting reinforcement steel is added at the end of the tendons. This is why the concrete needs to be so strong at 8,500 psi to counteract the strong force of these post-tension tendons. Now you run the individual cables that form your tendons, form up your beam, and get ready to pour. Once your concrete is hardened sufficiently, it's time to post-tension the tendons. And this tension is set by using a hydraulic jack pulling the cables a preset distance to achieve the desired amount of tension. And that black spacer sets the predetermined distance for the desired tension. Hydraulic pressure is applied to the jack, and the cables are pulled the distance of the black spacer, setting the desired tension. Remove the jack and spacer and trim the ends of the cable and get ready for grouting. Hook up your plumbing and fill the tendon duct with grouting. This prevents corrosion. And this also makes it a one-shot deal. There is no adjusting of these cables once this process is done. And this is not to be confused with the steel post tension rods used in the truss portion of the design of this bridge. Looks like the duct is full of grout. Trim off the plumbing and this section of beam is finished. So now as we go back and look at some of the NTSB B-roll footage of the wreckage of the bridge, you can begin to make out some of the components that we discussed. in the design of this bridge. Back here in Hong Kong on another long layover where the construction never ends, I hope this video gave you a better understanding of how post-tensioning was used in the failed FIU bridge design, and we can talk about the adjustable steel rod post-tensioning used in the truss design in a separate video. So as always, we're looking forward to your constructive comments and criticism in the comment section below. We'll see you here.